Lesson 3A is rate of change of linear and quadratic functions. So we have been doing quite a bit of rate of change, aka the slope, right? And we're going to continue looking at higher degrees of polynomials, starting with the quadratics. Okay, so first we'll look at a little bit of review and then see what happens when we start looking at a little bit more advanced polynomials as well. But you'll notice that the mechanics and the math that we're using are not going to change so much. All right, so just to review, if we have finding the slope of the secant line is the same as finding the average rate of change, right? Instead of calling it slope, we're calling it average rate of change. So when you see average rate of change, just remember we're just trying to find the slope from one point to the next. And we have a bunch of new symbols that might look different, but really nothing has changed mathematically. So like the change of x, right? All that means is how far is it from A to B, or B minus A. It has not changed. Same thing here. This right here, the delta y, that's just going to say the y value you get from B and minus the y value you get from A. Notice how we use the function notation. We're not really using y2 and y1 anymore, but the math is identical. So just keep that in mind as you're going through here, is that you already know how to do this mathematically, right? It's more of understanding this new language and that there's different symbols that we're using now that you haven't seen before, and we're just really trying to reinforce that and get used to it. Okay, so as we go through a few examples, just keep in mind that you probably know this in how to do most of these already. Just focus on using the new language more than anything else. Okay, so this says sketch a secant line. Remember, secant just means 2 points, by the way. So when you see secant line, that's a line that goes through 2 points, and those are the 2 points that we're going to use to find the slope. Right? Again, we haven't seen the word secant too much in the past, but really it's the same thing you've been doing all along. So we go like this and draw our nice secant line. And it says find the slope of the secant line, so we can do that. And recall that we're trying to find the average rate of change, so we can say we'll use our old-fashioned notation for slope, which is m. So the slope of the secant line, or slope of the secant, is the same as the average rate of change, right? Average rate of change. And that is just the same as doing the x's on the bottom and y's on the top. Right? So I'm going to do 4 minus a negative 6 on top, and 3 minus a negative 2 on the bottom, and simplify my answer. So I'll have 10 on top, 5 on the bottom, which just equals 2. And that's the equivalent of saying like this line goes up to right 1, up to right 1, right? So just keep that in mind. We already pretty much know this. The slope of the secant line is also known as, we already kind of gave it away, right? Average rate of change. So if you feel like we're just repeating ourselves from previous sections, that's okay. We're really trying to get used to this new language, average rate of change. And we can say it even more succinctly, like, well, what is this average rate of change of what? Well, of the function and we say over the interval, and we just say the x's that we used from -2 to 3. From -2 to 3. There we go. So that's a review problem using a graph, right? And if we just have an equation, like on the next one, that's okay too. So we don't actually have to have the graph to do these. Now let's just look at the function. They say g of x, and it's x plus 4 and x minus 2, and they're being multiplied. Now you want to know right off the top here that this is a quadratic. If we multiply this together, you have x squared minus 2, oh no, plus 2x minus 8, right? So if we multiply this out, x squared would be plus 2x minus 8. So this is a parabola. It's good to know just by looking at this that you know approximately, well, what kind of graph is this? So that looks something like this, like a U shape. Just simply because I have the highest degree is to the second power. I know it's going to look something like this. All right, and I'm trying to find the slope of the secant line from -1 to +2. So that looks something like this. Let's say like -1 is right here and +2 is right here. I'm just finding the slope of that line. So it's important to know what these questions actually mean before you just start trying to get the answer. All right, and this notation just says, it's -1 times, well, whatever the y coordinate is when you plug in -1. So when you see this notation, g of -1, it means you got to plug in -1 into here to get the answer, right? And here we have to plug in +2 into here and get the answer. They're not giving it to us like they did on the last problem. So let's start doing that. Let's find g of, let's go to green. Let's do this. Okay, let's find that first. So what's the y coordinate when you plug in -1? So that's going to be -1 plus 4 times -1 minus 2. So that equals 3 times -3, which is -9. So one of the reasons we like this notation, function notation, is because we have the x coordinate and it gives us the y coordinate. And we can see we got this y coordinate, -9, by plugging in -1. So it gives us our first coordinate, -1, -9. And we just need to repeat this process, and then we'll have two coordinates, and then we can find the average rate of change. So let's find g of 2 by plugging in 2. That's 2 plus 4 times 2 minus 2. All right, and that's going to be 8 times 0, which is just 0. So just like on the last one, we plugged in 2 for the x value. We got an answer of 0. So it means g of 2, the y value when we plug in 2, is equal to 0. So now we have the coordinate 2, 0. So now we can actually find our average rate of change and complete the problem. So my average rate of change equals, do 0 minus -9 over 2 minus -1, which of course is just 9 over 3, which equals 3. So the average rate of change of this line that we kind of sketched, this isn't an accurate sketch, but basically it says the slope of this line is 3 over 1, or just 3. That's what this number represents. So it's very important to know, after we get an answer, what does that answer actually mean? In past classes, you probably just focused on getting the number, and you said, I got the number, and I'm done with the problem. Moving forward in pre-calculus, you have to know what your answers actually represent on a graph. Even though there's no graph given, we can at least understand what our answer actually means. All right, so let's practice this a little bit more, but let's look at rate of change several times in one problem. And we kind of did this already, right? We looked at this in the last section, but we're going to look at what is the rate of change within the function. So we're going to find the rate of change of the first two, and that's what this means right here. And it says from -2 to -1, that's what this is. So use these two coordinates, -2, -7, and -1, -5, and then just repeat the process for the next two and the next two. And we did this already, but we didn't really give a reason why we're doing it, and that today we will have that reason. So pause the video, see if you can just find the rate of change for each one of these, and show a little bit of work, and go from there. Okay. All right, so go ahead and do that. Be right back. All right, so the first one, right? These intervals, remember, these are the x's, right? These are going to be the values that are on the bottom of our problem. So I know, like, this is going to be -1 minus a -2, and then I just need the y coordinates that go with these numbers. So what goes with -1? It's -5 minus what goes with x equals negative 2, that's negative 7. Alright, so we have, looks like 2 over 1, which just equals 2. And then repeat the process. These are the x values, so it's 0 minus negative 1. So I'm going to have negative 3 minus the y value that goes with negative 1 is negative 5. So we have 2 over 1 again. Notice how they're the same. Okay, so we'll do from 1 to 0. So we'll have negative 1 minus negative 3. So we'll have 2 over 1 as well. And then lastly, you could probably guess what's going to happen here. We have from 1 to 2. So we'll have 2 minus 1. And then it'll be 1. And we have 1 is negative 1. So we get 2 over 1 as well. So the fact that these are all the same is what we're interested in today, right? What makes this important? Like, well, this will tell us, number one, that these coordinates make up a certain graph, right? And if these were different, that tell us something else. So the fact that these are all the same tells us that this is going to come out to a nice first degree polynomial. The equation of this, if I was trying to find an equation of h of x, right? Equation of h of x is going to be something of a first degree polynomial because the first rates of changes are the same. Okay, here's what that means. Oh, first degree. Not change. First degree. AKA something in the format of mx plus b, a straight line. So it's called a first degree because the exponent of x is 1. Right? So if we have the rates of change turn out to be all the same on the first try through, we do all this over equal intervals, right? These are all equal intervals, meaning these numbers are all 2 from each other, right? 1 or 2 from each other, or 1 from each other. And we get those same rate of change. So what does that say about what is the change in the average rate of change? So how fast or how much are these changing from each other? They're not changing at all, right? They're staying the same, meaning subtract those, you'll see the average rate of change of the changes are 0. Okay, so when you see change, when trying to find the change of, that's a lot of subtraction. Just like when we found the average rate of change here, we did a lot of subtraction. Subtraction of the y's over subtraction of the x's, right? And then we did a subtraction of each of those. 2 minus 2 came out to 0. Right here, these came out to 0. So the change in is always going to be subtraction. So that's what they're asking here. So we can say something like the average rate of change, or the AROC, of h of x is constant. There's the magic word, constant. Notice I'm going to put that's equals 0 or same number. These are the same number, or that the average changes are equal to 0. Okay, so we can say that 2 different ways. So the rate of change of the rates of change is 0. Right? The rates of change of the rate of change is 0. So what happens if these do not come out to be the same? Let's look at that on the next one. So we can go do the same process here. You can pause the video. Once again, find the rates of change for each equal interval. Okay, so go ahead and do that. Okay, so let's do this once again. Negative 1 minus a negative 2. We'll have negative 1. Y value is 3 minus 11. So here we'll have negative 8 over positive 1, which is just negative 8. Okay, next. Let's do green. All right, let's do the next one. We have 0 minus negative 1. So we'll have negative 1 minus 3. So here we have 2. No, we don't. No, we don't have 2. We have negative 4. Yeah, negative 4 over 1. So that equals negative 4. So notice how these are not the same. All right. Let's keep going. We have 1 minus 0. So 1 is negative 1. Minus 0 is negative 1. So we'll have 0 over 1, which is just 0. And lastly, we'll have 2 minus 1, which is going to be 3. And 1 is negative 1. So here we'll get 4 over 1, which equals 4. So notice how these are not the same. So this is not going to be, these coordinates are not going to make up a first degree polynomial, aka a straight line. Because unlike the one before, right, these rates of change being the same means it's the slope of a straight line. The first degree polynomial, it's going to come out to be that type of equation because this first set of rates of change are all the same. But here, the first set is not the same. So this will not be a straight line. So this is why we look at the difference of the rates of changes. We find the change in the rates of change. So we're finding the changes between, let's say, those two. So negative 4 minus a negative 8 equals 4. And then we do the same thing here. We'll do 0 minus a negative 4. That also equals 4. And lastly, we'll have just 4 minus 0. That equals 4. So you notice the change in the rates of change. This is where they're all going to be the same. Notice how this was the first time we did this, right? Rates of changes. And this is the second time. So what this means when these are all the same is that this is a second degree polynomial, aka something with a x squared in it. All right, so if we plotted all these points, it's going to come out to look like some sort of parabola, either facing up or facing down, but I know for sure because the second round of rates of changes are the same that we have a second degree polynomial. Okay, very important to know this, understand that concept without actually having to graph it. And that's the whole thing. We're trying to avoid graphing these and just get this answer or get this conclusion without the need of graphing. So what we would say, the average rate of change, what is the change in the average rate of change, right? They're asking about this. So that change in the average rate of change is 4. And we could say average rate of change of f of x, right? That's the name of the function, is 4 as well. Be a little more specific. All right, good. Hopefully this is working for you. So what does this mean? Why is this important, right? This is going to tell us not only if the second set of rate of changes are all the same, it's going to make a difference if these are going up or going down. So you notice from, if we go back and look at this, from negative 8 to negative 4, it's increasing. From negative 4 to 0, it's increasing, right? It keeps increasing. These are all positive. That's going to tell us another piece of the puzzle without actually graphing. Okay, so that's the next thing, is to look at this carefully and realize, is it getting bigger? Are all these getting bigger, or are they getting smaller? Okay, so if we go to the next page, we'll see what that actually means. So we're going back to concavity. Okay, so it says, in a quadratic function, we can determine the curvature or concavity of a graph by considering the average rate of change over the equal intervals, and sketch slopes at each point shown below. Okay, so what we're doing here, so I'm going to sketch some slopes, and you might want to use a straight edge for this. Okay, so if we have something that's concave up, in other words, this is opening up. This is what concave up means, right? If it's concave up, what does that tell us about the actual slopes, right? So if I look at this, what is the approximate slope of that line? And we could say, how about this is like a -2. And if I go an equal interval to the right, and I found the slope of this line, we could say that that is +2. And if I went further over, I could say like this. Now this is getting steeper, right? And that's going to be like a +4 slope. And this would say, if I use a tangent line, I guess not a good tangent line. There we go. If I use that as my tangent line, right there, I could say that has a slope of 6. So you notice that these are increasing. This goes from -2 to +2 to +4 to +6. So it's increasing more and more and more, and that's how we know we have a concave up situation without actually graphing. Okay, that we were going to figure this out without actually graphing. So going back to the last page, I can tell, since these are going up and increasing, that this is not going to be concave down, that it's actually going to be a graph with concavity or curvature opening up. And likewise, if we have a concave down situation, right, we'll have something like this. Let's say this is a slope of 2, and let's say this is a slope, this is now negative, so that's going to be a -2 slope. And we could say this is a slope of -4, and this tangent line over here is a slope of -6. Well, from +2 to -2, it's going down. From -2 to -4, it's getting smaller, right? And going smaller from -4 to -6 is getting smaller. So this is how we know we have a concave down situation without actually having a graph. Okay, so these slopes are decreasing, right? We're going from positive, gets negative, more negative, more negative. So I know I can get a concave down graph from the slopes, looking at the slopes and seeing if they're increasing or decreasing. All right, so let's look at one more to understand this completely. So we're going to find the average rates of change once again, but then consider, like, are the slopes increasing or are the slopes decreasing? And then we can say whether it's concave up or concave down, all without actually graphing this, right? So we don't want to actually graph these numbers and see it. We want to do this by the numbers, or analytically is the fancy word for this. So we're doing everything just by the numbers. So let's do one more time. You can pause this and go ahead and do all the calculations. Okay, so I did all the rates of change, and now it says find the average rate of change over each of the intervals. Did that. And let's look at, well, how much are these changing? So we can see quickly this is not going to be a first degree, right? These are not the same number. But if I do this next round, I do 3 minus 9, I get -6. If I do -3 minus 3, I get -6. If I do -9 minus a -3, I also get -6. Right? So the fact that this comes out right here, that the change in the average rate of change is negative. All right? It's negative. That means these are getting small. It's the same as looking at these and noticing that these are just getting smaller and smaller, from 9 to 3, 3 to -3, -3 to 9. Right? So it tells us, number one, it's a quadratic because these are all the same number, and number two, that since they're negative, that means it's decreasing, right? Which also means, like this one right here, the slopes are getting smaller. It means that our graph will be concave down, and we can get all that information without actually graphing it, and that's the most important part. So right here it just says, what do you know? It's about the average rate of change. All right, it is decreasing. All right, so you can just say the average rates of change are decreasing, getting smaller as we go down. And what does this tell us about the concavity? Well, if it's decreasing rates of change, right, it's going to be concave down. So just say the function, or h of x, let's just say that. Let's just say h of x is concave down. Okay. So these go hand in hand. If we have decreasing rates of changes, automatically that's going to mean concave down. So I have to highlight the whole thing. So that's the big takeaway about this lesson, is just knowing that pattern particularly, right? Without actually graphing it. So we can have very large numbers, do some calculations, and still come to the right conclusion without actually having to graph any of it in the first place. All right, and that's it for this video.